Somewhere in the darkness between the stars, an object is racing through space that no telescope can see. It has no light, no heat, no warning signal. It's a stellar mass black hole, roughly 10 times heavier than our sun, yet only a few dozen kilometers across. It's tearing through the galaxy at 500 kilometers per second, 1,000 times faster than a passenger jet. Objects like this are called rogue black holes, once part of a binary star system, left alone after a supernova explosion, drifting through the Milky Way ever since, invisible and silent. Today, one such wanderer is heading straight toward our solar system, and no one on Earth knows it yet. The solar system's first boundary lies almost 2 light-years from the sun, the Oort cloud, a vast sphere of ice and rock left over from the formation of the planets. This is where the black hole crosses the outer threshold. Its gravity is negligible by earthly standards, but at a distance of trillions of kilometers, that's enough to tear millions of icy bodies loose from their orbits. The entry trajectory cuts at an angle to the plane in which the planets orbit, meaning this encounter won't be fast or glancing. The black hole enters the system slowly, along an arc stretched across decades, disturbing everything in its path. And the first victims won't be the planets, but the countless comets and asteroids that have drifted quietly at the very edge of our home for thousands of years. The gravitational disturbance moves through the Oort cloud like a wave through still water. Icy bodies that had remained in place for billions of years suddenly break loose. Some plunge deeper into the system, others are hurled into interstellar space forever. Some of these would have become future comets, ones that might have lit up Earth's sky centuries or millennia from now. Now their paths are unpredictable. Astronomers detect a sharp spike in activity at the system's outer edge. Objects that had followed stable orbits for tens of thousands of years suddenly shift course. It's the first observable sign that something massive and invisible is entering the solar system. And as it moves closer to the sun, the destruction will only accelerate. Years after the first contact, the black hole reaches the outer edges of the planetary system, and here, its presence can no longer be ignored. Neptune, the outermost gas giant, begins slowly drifting from its centuries-old orbit as the gravity of the uninvited guest pulls it off course. Pluto and the other dwarf planets of the Kuiper Belt react even more sharply. Their orbits turn chaotic, and some bodies are already on the verge of leaving the system forever. For astronomers, this is an alarming signal. An object massive enough to shift a planet the size of Neptune cannot be an asteroid or a comet. The calculations point to only one explanation. A compact, supermassive body has entered the system, a black hole, and it won't stop at the outer edge. What follows is chaos. Uranus tilts even further from its already strange rotational axis. Saturn, whose icy rings took billions of years to form, begins to show tidal distortion, the black hole's gravity pulling different parts of the ring system with different force. Jupiter, the most massive planet in the system, is still holding its orbit, but with every passing year, the approach shrinks the distance further. The entire architecture of the solar system, built over 4.5 billion years of evolution, starts to collapse like a house of cards. The orbital resonance that had kept the planets in stable balance for centuries breaks down, and what was once a predictable dance of planets around a star turns into uncontrolled gravitational chaos. While the planets drift from their orbits, astrophysicists on Earth are racing against time. Supercomputers spin up n-body simulations, models that calculate the gravitational interaction of every major body in the system simultaneously. The goal? Predict what happens next. The results are grim. With an object of roughly 10 solar masses, the closer it moves toward the center of the system, the faster the chaos compounds. The probability that even a single terrestrial planet retains a stable orbit drops sharply with every new model run. One of the project's lead astrophysicists sums it up in a single line. What we're witnessing isn't a gradual shift. It's the beginning of the total gravitational collapse of a system that took billions of years to form. And this is only the start.
On Earth itself, the effects are felt long before the black hole ever draws near. Scientists record 15 noticeable anomalies. The length of the day starts to fluctuate, gravitational disturbances slightly altering the planet's rotation speed. Earth's axial tilt, stable for thousands of years, begins a slow drift, threatening sharp climate shifts down the road. The planet's magnetic field, our shield against solar radiation, shows unexplained fluctuations in strength. Ocean tidal forces intensify with no visible cause. Coastal water levels behave unpredictably. Atmospheric pressure shifts in sudden jumps at multiple points on the planet simultaneously. On their own, each anomaly might look like a coincidence. Together, they add up to only one possible conclusion. Something massive is approaching, and Earth can already feel it.
The first truly massive casualty is Jupiter. The gas giant, containing more mass than all the other planets combined, turns out to be not massive enough to resist the gravity of the rogue black hole. The upper layers of its atmosphere, hydrogen and helium accumulated over billions of years, begin tearing loose, spiraling toward the invisible center of attraction. This is how the first accretion disk forms. Gas, heated by friction and compression, starts glowing for the first time in this entire encounter. What was once a completely invisible object now becomes visible, though too late for it to change anything about what happens next. Vector calculations show Jupiter's mass is no longer enough to break free of the gravitational grip. The giant is doomed. What happens next, physicists call spaghettification. The difference in gravitational pull between Jupiter's near side and far side becomes so extreme that the planet is literally stretched into a long, white-hot thread of gas and plasma. Within hours, an object that took billions of years to form turns into a spiraling stream of matter, coiling around the invisible center. The accretion disk ignites with unbearable brightness, temperatures in its inner layers reaching millions of degrees from the friction of infalling gas. For several days, this disk becomes the brightest object in the entire solar system, outshining everything except the sun itself. From Earth, it looks like a blazing new star suddenly flaring in the night sky. Beautiful and absolutely lethal. The blinding light of the accretion disk isn't just a spectacle. Gas heated to millions of degrees emits a powerful stream of X-ray and gamma radiation, invisible to the human eye, but extremely dangerous to all life. Orbital observatories, including the Chandra X-ray telescope, detect a radiation spike orders of magnitude above the background level, typical for this part of the sky. Earth's magnetosphere, already weakened by the ongoing gravitational disturbances, deflects part of this stream, but not all of it. Satellite communications begin to fail. Radiation levels in high orbit climb to dangerous values. It isn't a direct threat to the surface yet, but it's a clear signal. Whatever is happening in the system is generating energy on a scale humanity has never encountered before. Earth's ultimate fate depends on a single variable, the exact trajectory of the black hole's passage relative to our planet and the sun. The calculations produce two fundamentally different scenarios. In the first, Earth receives a gravitational kick that flings it onto a far more distant, elongated orbit, or ejects it from the system entirely. In that case, the planet faces slow freezing. Surface temperature drops, the oceans lock into ice, the atmosphere gradually condenses. In the second scenario, the kick is directed inward. Earth falls off its orbit toward the sun. The result is the evaporation of the oceans and the transformation of the surface into a scorched wasteland long before any actual impact. Both outcomes are equally fatal for the biosphere. The only difference is whether the planet burns or freezes. In the scientific community, the debate stops. The numbers speak for themselves. Regardless of which of the two scenarios unfolds,
the final probability of Earth's biosphere remaining habitable is calculated as effectively zero. None of the known mechanisms, not the magnetic field, not the atmosphere, not the distance from the sun, can compensate for gravitational disruption on this scale. In the scientific literature, a term starts appearing more and more often: rogue planets, worlds torn from their systems and doomed to drift through interstellar emptiness, with no star, no warmth, in permanent darkness. The irony is that this same term had previously been used for other planets, destroyed by the exact same kind of wandering black holes elsewhere in the galaxy. Now it applies to Earth. After passing through the inner part of the system, the black hole's trajectory keeps changing under the influence of the sun's own gravity. From here, two final outcomes are possible for the entire system. In the first, the object isn't moving fast enough to escape the star's gravitational well and settles into a long, elongated but bound orbit around the sun, becoming a permanent, invisible companion to our star for millions of years to come. In the second, the velocity gained during the flyby exceeds escape velocity at this point in the system, and the black hole, carrying with it the debris of the destroyed planets, leaves the solar system forever, continuing its lonely journey through the Milky Way's spiral arm in search of its next victim. Decades after the first contact, it's finally possible to take stock of what remains of the solar system. Mercury and Venus, the two planets closest to the sun, are either consumed by the white-hot remnants of the accretion disk or flung from their orbits for good. Earth, depending on the scenario, is either boiled away or turned into a frozen, lifeless sphere. Jupiter, once the largest planet in the system, is torn apart and scattered into countless rings of debris. But not every world is destroyed outright. Some, including the outer icy bodies and possibly Saturn and Uranus, are hurled beyond the system's edge by the gravitational maneuver. These are now rogue planets, lone wanderers with no star, drifting through interstellar darkness, just as the black hole itself once drifted, before it began this entire chain of destruction. What we've just described isn't an isolated case, and it isn't hypothetical fiction. According to current astrophysical estimates, tens of millions of stellar mass rogue black holes drift through the Milky Way alone, remnants of long extinguished supernovae that lost their stellar companions. Data from space observatories, including the Fermi telescope and the Gaia mission, allow astronomers to map only a small fraction of these invisible wanderers, detected through their gravitational effect on nearby stars. Catastrophes like the one we've just walked through have already happened, and are happening right now, somewhere else in our galaxy, in other planetary systems we don't even know exist. Our solar system is just one among billions, and statistically, sooner or later, the odds may catch up with any one of them. The black hole continues on its way through the galaxy, carrying with it, in orbit around itself, the debris of what was once a thriving planetary system. Behind it, only emptiness remains where Earth used to be, and scattered fragments of gas giants thrown across billions of kilometers. And somewhere far away, in the pitch darkness of interstellar space, drifts what used to be our home, now just another fragment among trillions like it across the galaxy. It might seem like the odds of this scenario are vanishingly small, but on the scale of the universe, where time is measured in billions of years, a vanishingly small probability eventually becomes reality. If you enjoyed this journey into one of the darkest possible scenarios for our planet, subscribe to the channel so you don't miss the next What If.